Okay, welcome everyone. I'm a little busy today, so I'm going to have to record the lecture for today's class on meta-analysis. And don't misspell it. You maybe end up doing a meat analysis. The idea of a meta-analysis comes from evidence-based medicine. And so let's first start talking about what that is. Sackett in 1996 described evidence-based medicine as the conscious, explicit, and judicious use of the current best evidence in making decisions about the care of individual patients. It means integrating individual clinical expertise with the best available external clinical evidence from systematic research. This branch of evidence-based medicine aims to make individual decision-making more structured and objective by better reflecting the evidence of research. And this is started in the last century, and it's continued on in that most of the medical research that doctors will pay attention to are evidence-based. What happened before that? That just seems so logical. How could doctors work before that? Well, before that, doctors made decisions based on a mix of several things. Clinical experience, that is their own personal subjective experience. Physician intuition, that is their subjective intuition. And then before evidence-based medicine, they called it science-based medicine or research-based medicine. And the research that they were basing their decisions on was from a small number of studies without internal validity. That is, very few studies had randomized controls and with very limited external validity. You don't really need to say much about internal validity if you don't have randomized controls. You really don't have good internal validity at all. And external validity, yes, that's something that we should talk about. In medicine, you'll see in the history of medicine many studies, many famous studies that have said something about how to treat people was only conducted on white people. Or on males, or on one genetic group. And what researchers found over the last several decades is that by doing research on one ethnic group, one genetic group, one gender, you're not developing the appropriate external validity in your studies to be able to generalize your results to everybody. And in fact, in many cases, gender has a very important effect on many research outcomes in medicine. And ethnicity and gender group also have significant impacts upon the outcomes of medical studies. So these were the problems with medicine about 25, 30 years ago that evidence-based medicine decided to fix. And I've shown you this before and deserve to show you this again. This is the hierarchy of scientific evidence, and this is really what we're talking about in terms of evidence-based medicine. That is, before evidence-based medicine, doctors were working with animal trials, with cross-sectional studies, with case studies, and maybe some cohort studies, but very few randomized controlled studies, and then very few meta-analyses or systematic reviews. And that's because in general there wasn't that many studies on the same disease, so there wasn't enough to do a meta-analysis on. And then also, meta-analysis is generally a new thing. When I was in graduate school in the 80s, some psychologists didn't even know what it was because it was so brand new. So, by the time the 1990s rolled around, oh, thank you, motorcyclist. Now meta-analysis was being talked about by psychologists, and the medical profession were getting hip to it. So the whole idea of this pyramid is that we're really talking about recognizing that a medical study or a scientific study is not a scientific study, not like every other scientific study. That is, some studies are weaker in terms of their scientific evidence, some studies are stronger, and then some methods of summarizing many different studies are stronger than other methods of doing this. So now that we've talked about the need for a meta-analysis, let's define what it is. Huke in '88 said that the statistical analysis of a large collection of analysis results from individual studies for the purpose of integrating the findings. Oops, I'm sorry, that was Glass 76. And Huke in '88 defined the meta-analysis as a statistical analysis which combines the results of several independent studies considered by the analyst to be combinable. And that's very important. We'll get back to that in a couple of slides. But what we're doing is we're looking at a large group of already completed studies, and what we're doing is we're treating the results of each individual study as like one observation, and then we're going to do a statistical analysis on that distribution of results of studies. And Huke also says that the same thing is the statistical analysis that combines the results of several independent studies, and that has some benefits that we can take advantage of. So stages in so one of the first things you need to do a meta-analysis is collect all the articles that you can find on a phenomena, and this is a good opportunity to differentiate the literature review from the systematic review and the meta-analysis. In all three of these types of studies, you're overviewing or overseeing the results of several studies on the same phenomenon. In the literature review, what you're doing is you're doing this very subjectively and in a narrative fashion. So you formulate a problem that is there, like for example, there's a lot of studies on the fundamental attribution error. Somebody needs to write a review of them, and usually that's a good example of the problem formulation for a literature review. Or I'm going to look at the results of studies on the defensive attribution analysis, defensive attribution theory, and basically make a conclusion about the effects of personal similarity. Then now that you know what you're looking for and you lay out the articles that you're looking for, you search the literature, and then once you have the articles, you read the articles, you look for patterns subjectively, and then you write it up in a narrative format. Systematic literature review is very similar to that, except that the search for articles is more systematic. And this has happened in the last 30 years since there has been searchable databases for psychology and other research fields. Back before the internet, there was a stack of psych abstract journals in paper bound in the library, and you had to go through them and go to the index of each year and look up your topic, and then go and look at the abstract in that year's publication. That was a very slow process. Now you can search from your home in your pajamas for articles that meet a very, very specific definition of different requirements. That is, the years, the types of subjects, the keywords, and that's what you do with a systematic review. You use the computer to identify as many and all of them as possible, but then in a systematic review you still then continue on and do the subjective literature review where you read things and then draw a conclusion yourself. However, with a meta-analysis, you first do a systematic review. That is, you allow the computer to search for all the articles that meet your criteria. And then you collect the data from those articles. So sometimes the articles are written and the results sections are written so that the data that you need, the means, the standard deviations, the inferential statistics are available to you. You bring them all together and you do data analysis, specific data analysis that have been developed for meta-analyses, and then you present the results. And this confuses some people, so we can talk about the Venn diagram of all review articles here. And within all review articles, some are systematic reviews, and some of those systematic reviews are meta-analyses. Another way of thinking about the difference between a systematic review and a literature review is by definition. Systematic reviews are high-level overviews of primary research on a topic that identifies, synthesizes, and appraises high-quality research. Its goals is to answer a focused clinical question and try to eliminate bias. The question it's asking should be clearly defined by PICO, or patient problem intervention comparison outcomes, components, the specific eligibility criteria, the systematic search strategy, the assessment of the validity of the findings, the interpretation and presentation of results, and the reference list. It takes a long time to do a literature review, and it allows practicing clinicians to access high quality information, and it supports evidence-based practice. A literature review, on the other hand, qualitatively summarizes evidence on a topic using informal or subjective methods to collect and interpret studies. It provides an overview of the topic, can be great for a general topic or a specific question. It has the normal components that you see. One or more authors would do this. It takes much shorter time to do a literature review, and it provides a summary of the literature on the topic. But it doesn't provide the high quality information that systematic reviews do. Getting back to the meta-analysis, the goals of the meta-analysis are to answer questions such as, what is the direction of the effect? That is, we have a phenomena, we have an IV and a DV. As you go from one level of the IV to the other, what is the direction of the effect on the DV? Does the DV go up? Does the DV go down? What is the size of the effect? And now we're talking about effect size. Is the effect consistent across studies? There are general reasons why this is the case or not, and that's very telling when you look at these reasons why they're consistent or not. Combined result, you can combine the results quantitatively. That is, you can dump several studies into a bin, a theoretical bin together, and you can look at the results based on what this new category you created says, or you could just look at the entire field of studies that you have and make a general conclusion. And finally is to investigate heterogeneity. That is, to examine why there are different results among studies. What are the reasons for these different results? I mentioned combinable before. Now I need to really define that. We say that articles are combinable when you have more than one study that examines a single phenomenon. and that you look at different study characteristics and conclude that they are unlikely to affect the effect. So I'll give an example in just a minute, but combinable means that if we are going to dump all like 100 studies into one bin together, one theoretical stat bin, and say that they're all the same study, that has benefits and that can help out. But it only has benefits if they really are combinable, and that is if they're really looking at the same phenomena. And whether or not the studies are done exactly the same or slightly differently may affect if they're combinable. And the only way to tell is to investigate the differences. Look at the different studies and look at the different data from those studies, their results, their methods, to try to determine if they are truly combinable with other studies. And of course, this is more subjective than objective, and this is where one of the major problems with meta-analyses occur. That is, if a meta-analysis that has been published will be questioned, it's mainly about the issue of combinability, whether or not we can say two studies that we're looking at are essentially the same. Let's take a look at this table to give a brief illustration of combinability. So I'm looking at the weighted effect sizes here, and then I can total them up, and then I can divide them by n and get an average weighted effect size, which is generally what we do in every meta-analysis. And the question is, are these studies combinable? Or are there differences that make these uncombinable, that they should not be placed in the same bin? And in fact, if we would investigate further, we would look at the methodology and see that the methodology of these studies is different. Smith and Merriweather used concurrent concurrent validity methods, and Jones and Johnson used predictive validity methods. And so that was a difference underlying many of the differences in these studies. And so perhaps we should not combine those four studies together and look at this mean correlation of the weighted effect size, because these studies are coming from different methodologies. And indeed, when we look at the weighted effect sizes, we see that the concurrent methodologies have a much stronger weighted effect size, and the predictive has an extremely variable effect size. Okay, so now we see that there are differences in the methodology of these studies. Smith is concurrent validity, and Merriweather is concurrent validity, and Johnson and Jones use predictive validity methods. And we see that the concurrent validities, we only have two of them unfortunately, are relatively close to each other in distance. However, we see that Jones and Johnson, their weighted effect size, it has a great deal of validity, variability, 99 versus 8.9. So given that it's a different methodology, given that our two studies for concurrent validity are relatively close to each other, and given that our two predictive validity methods are far away and have a huge variability, we may want to decide to say that this is non-combinable. And you'll see exactly what I mean as we get to the big example. And here's the big example. It's a case study. IO psychologist is working for a manufacturing plant. The current employment test correlates 0.25 with job performance. It's a robust correlation for both predictive and concurrent studies. People are talking about a new test, and so the IO psychologist does a literature review and finds 4 studies using the new test. And so here are the 4 studies using the new test. So let's just go back for a second. IO psychologist, and so the current test he's using has a correlation of 0.25 with job performance. That is the employment test. You go in, you want a job, you go in, they give you the employment test, and then they score it, and based on the score they give you a job or reject you. And they do this because they know that there's a correlation between your score on the test and your performance on the job. And doing this saves money for the company because you're only hiring people that will do a good job. If people are talking about a new test which may have a higher correlation than 0.25, then you may want to find it, because every time that correlation increases between your employment test and job performance, you're saving your company money. And in fact, if you work it out, you're saving them tens of thousands of dollars for each 1/100th of a correlation point. So you do a literature review and you find 4 tests. Smith is a correlation of 0.22, Jones correlation 0.33, Johnson 0.27, Merriweather 0.18. And so remember, our current test has a correlation of 0.25. So if we just use a voting method, we can see that, and remember again, these are all tests of the new employment test, and how well the employment test predicts job performance in this industry. And so we could just use a voting method, and so if we do that, is 0.22 higher than 0.25? No, so it's not better. Is 0.33 higher than 0.25? Yes, so this test does seem to be better based on Jones. 0.27, is that higher or lower? Yes. 0.18, is that higher or lower? Lower. No. So basically they're split 50-50. From just looking at the effect sizes, and remember R is an effect size, looking at the effect sizes, we see that there's no better or worse set of results that says that this test is better than the one I'm using, or worse. They're split, on this voting method. So if you just do a yes/no type of tabulation, you're going to stick with your old test because it's not clear if this new test is doing any better. But we could do one better than actually looking at a voting method, and we could actually take the mean effect size, and if we do that, the mean effect size is 0.25. And so again, now we're saying, well, if we take the mean effect size of this new test, it's the same as the old test, so we shouldn't do anything. So the voting method and the mean effect size methods say that we shouldn't do anything. We should stick with our old test because this new test is just as good and not any better. However, the voting method and just calculating a mean is not anything like what you do when you do a meta-analysis. One of the basic things that we do in a meta-analysis is we look at sample size, because smaller samples have larger errors than larger samples, and so therefore smaller samples are less trustworthy than larger samples. And so we need to have some way of taking into account sample size when we're looking at effect size. And one easy way to do it is weight the effect size by the sample size, and you do that by multiplying. So we have Smith has 125 subjects and an R effect size of 0.22. we multiply those together. Jones has 300 subjects, 0.33, and we multiply them together, and so on and so on. 125 times 0.22 is 2.75. 300 times 0.33 is 99. 33 times 0.27 is 8.91. And 99 times 0.18 is 17.82. We add those up, and it gives us that. And then what we do is we divide by the sum of the n's. And so here we have the total number of subjects is 557. So we divide the sum of the weighted effect sizes by 557, and that gives us 0.275. And remember, the old correlation, or the correlation for the old test, is 0.25, and the average is 0.25 also. But once we weighted this, we see that the weighted effect size, the average weighted effect size, is doing better than our current test. Our current test is 0.25. This new test, the average weighted effect size is 0.275. So this is exactly what a meta-analysis is. You're basically looking at different studies and you're weighting them by the size of the sample. Because again, smaller sample sizes introduce more variability into the effect size, and so the effect size we see is less trustworthy. And for example, I believe we're going to see, let me go back and check. Yep. We're going to see that these two are predictive, and so Jones has 300 subjects, and their correlation is their effect size is 0.33, and Johnson has 33 subjects, and their effect size is 0.27. And which one of these, or let me clear this up, which one of these effect sizes, 30.33 or 0.27, is more trustworthy? And in fact, because of 300 subjects, the 0.33 is more trustworthy. And so given the choice of saying, well, is it just 0.27 and 0.33 average together? No, I would put more weight on 0.33 being the actual effect size, because Jones has more subjects, and so there's less variability or less error in prediction of this effect size. And we'll talk about that in a minute. So our first conclusion from this sample meta-analysis is weighting by the size of the study tells us that the new test will be better than the old. So we already know what to do. Based on this meta-analysis, we should switch over, and given like a large-sized national company and the normal turnover costs, I once calculated that this new correlation between the employment test and job performance would save the company about $500,000 a year, which is significant. But then what else can a meta-analysis do? And the answer is we can group studies based on variables or characteristics. And so I've been mentioning concurrent and predictive validity. Concurrent validity is where you have a predictor, that is mental ability test, given to higher workers. And then what you do is you correlate that with their current job performance. This method has poor external validity. because hire workers don't see this test the same way as job seekers. That is, when you're given an employment test as a job seeker, you're nervous, you're motivated, and so that's a very specific situation. When you're a worker and you're given a concurrent validity test, what happens is you're called into the IO psychologist's office, so you're getting time off work. Wow. And then you're taking a test, a paper test, which may be interesting, but it doesn't mean anything. It's not going to affect anything. So you're not motivated. So workers that are not motivated and they're not anxious like the job seekers, so there's poor external validity there. Predictive validity is when you take a predictor, that is a mental ability test, and you give it to job applicants. And then you hire all the job applicants, and then a couple months later you look at their job performance and see if there's a correlation between the predictor and job performance. And this has great external validity, and managers hate this because you have to hire everybody, and they're like, wait, we're giving them a job test, and then we're hiring them no matter how bad they score. That doesn't make sense. Well, that's why they hate it. But these are the two methods that we could use to generate validity data in an IO setting. And so we can expand our little table here like this by looking at, and this is what I showed you before, we could group the studies by predictive and concurrent validity. And so the concurrent validity studies, they have found that the average mean correlation, or the average mean effect correlation or effect size is 0.20. And remember, the test that we're using right now is 0.25. So these concurrent studies are telling us that this new test is worse than the one we're using now. However, when we look at predictive studies, we see that the average mean correlation is 0.32, which is much higher than the entire data set and much higher than the test that we're using now. So it would be a great test to use. And we can take that information and feed it back into our understanding of the difference here. That is, predictive validity has better external validity than concurrent validity. So it could be that the concurrent validity studies are being affected by the poor external validity of having people currently at a job taking the test and goofing off during the test and not taking it seriously. Whereas in a very realistic situation, we find a much higher correlation between that new employment test and job performance. So conclusion number 2, predictive studies with better external validity have higher correlation than concurrent studies. And so that's the second thing meta-analyses can do. They can look at different types of studies. And in this case, it's IO Psych, so we're looking at IO Psych stuff. But in meta-analyses I look at, they're looking at things such as date rape versus stranger rape, or in things like that. So you can classify studies in different ways. You can classify them in terms of when they were conducted during the 70s, 80s, 90s, OOs, the 10s. So there's all different ways that you can classify studies and do a meta-analysis to tell you if there's any effect of whatever you're talking about affecting the relationship between the IV and the DV. And then finally, meta-analyses can do something very important and expose a major research problem. This is known as the file drawer effect. The file drawer effect basically says this. First off, only significant studies get published. And I'll talk, I've talked about this, and I'll talk more about this next week. So only significant studies get published. Only studies which find an effect get published. That's just another way of saying only significant studies get published. Non-significant studies do not get published, and they're filed away in file drawers in labs. And I have like 8 or 9 studies that found no effect that are sitting on defensive attribution, and they're sitting in file drawers in my office, except that during the pandemic there was a flood in the psych department labs, and I think everything was destroyed. I don't know, I haven't been back to campus yet. But the file drawer problem is pretty interesting because, for example, here we have studies that were published, and the numbers I give you certainly indicate that they were published, but then there could be a whole set of non-significant low effect size studies out there on this new IO test that are just sitting in file drawers because they're not going to be published. So let's give that a shot. And so here's what we do. Here's our original set of studies, and these were all published. And then what I do during my meta-analysis is I try to find all of the published and unpublished studies. And so first, York College in York, Pennsylvania, their IO psychologist there published a study on this new test, and she had 100 workers in her experiment, and the correlation she found between the new test and job performance was 0.02. And I ran into her at a conference, and we were talking about this, and she said, "Oh yeah, I have something in my file drawer that was non-significant that I didn't publish." Leo Sammy Incorporated, a big marketing research firm, they did a study with 280 subjects, and they found 0.11 correlation, and they didn't publish it because they're in business and they're not going to share it with other people for free. But a friend of mine got a hold of it and passed it on to me. York University in Britain did a study. One of the researchers there did a study with only 35 workers, and they found a 0.32 correlation. And finally, the Wilson Group, which is a group that I used to work with, not really, but it was a small consulting firm. They did a study on this new test with 68 subjects and found a correlation of 0.09. And so what we've done is we've looked at a special type of difference. Are they published or are they not? And so now we can make conclusions about, well, what's going on if something is published or not. Well, as we said before, the average weighted correlation is 0.27 or 0.28 for this new test. And that certainly says use it because it will save my company money. However, that doesn't take into account all the studies that had non-significant results. And so when you do that, the weighted average correlation is 0.1, and that is a really frowny face because that is much, much lower than 0.25, which is what the current test does. And then when we dump everything in together and say, okay, given the fact that we have these file drawer studies that weren't published, and we have these published studies, what's the average mean what's the average mean correlation for everything that we have? And look at that, 0.19. That's less than 0.25. So all things considered, we should not move to this new employment test because it does a worse job of predicting who will be a success and who will be a failure. And looking at the a file drawer effect is one of the beautiful things about a meta-analysis. Oh, okay, I want to skip this. So let's skip this. Okay, so how do we go about representing or summarizing the results of a meta-analysis? Uh, we could do something called a forest plot, and sometimes this is called a blobogram because it generates blob, but it's a graphical display of a meta-analysis data, and the size of the boxes indicate the weight of the study, that is the number of subjects in the study. And the diamonds indicate, or the one diamond, excuse me, indicates the meta-analysis effect, that is the result of the meta-analysis. Just as we were saying that the result here was 0.19, that's what we mean by where the diamond is. And finally, these are the results are listed in odd ratios. And this is a non-parametric effect size, and I'll get into that a little bit more later. So here's a forest plot or a blobogram. There's the blob right there, and again, it's using odds ratios, which are the measure of effect, and IV random just means whether it's a fixed or random model, and we've already run into that in ANOVA. So if you really want to know what that means, I'll tell you individually, but we won't go into it here. And then the whiskers here indicate the 95% confidence interval of where we would find the effect of a single study. So this is a single study right here. This is a single study right here. This is a single study right here. This is a single study, single study, single study, single study, single study. And then this here is the average of the effect size. And so the very average of the effect size would be about a 1.4 on the odds ratio scale. And the width of this diamond is the 95% confidence interval of where we, at a p of less than 0.05, where we think that average overall score for the meta-analysis should be. It could be as low as 1, or it could be as low as 1.25, or as high as 1.7 or 1.75. And another thing, as I mentioned, this is the odds ratio that the study itself found, and this is the confidence interval, or the error bars, in that there's a 95% chance that the value, the sample value that the one study found, could be as high as up here or could be as low as down there. And it looks like what they're looking at is a scale where everything below 1 indicates no cognitive decline, and everything above 1 indicates a cognitive decline. And so what this is looking at is possibly the effect of some type of treatment or some type of disease on people, on older people's cognitive decline. And we're seeing that based on 1, 2, 3, 4, 5, 6, 7, 8 studies, they are concluding, based on the meta-analysis, that there is an odds ratio effect of about 1.4 that whatever's going on will cause cognitive decline. And that's the overall result of this meta-analysis. Also remember, the size of the box indicates the number of subjects. And notice here, the bigger boxes with more subjects have shorter whiskers. And this big box up here has very short whiskers. This study here with a little box has long whiskers. And that's again because smaller sample sizes in a study mean that their results are more unreliable. And here's another forest plot, and this is for the Macbeth effect. Remember Lady Macbeth, out damn Spot, and she kept on scrubbing her hands because she had killed not Macduff. Who did she kill? I forget. Macduff was the cop, more or less. But she kept on scrubbing her hands even after the blood was gone. And so here's several studies on the Macbeth effect, and notice it's from the 2000s and 2014s. These are all replications, by the way. And this is an example of looking at studies that have replicated a famous effect that we assumed was replicable, and now we're actually going to test it. And we're going to test it with several studies, and then how are we going to compare those studies with each other? Simple, through a meta-analysis. And so all these studies looked at the Macbeth effect, and they used Hedges G, which is more or less Cohen's D for small sample sizes. And so we have the N, the effect size, and then the 95% confidence interval of what that effect size should be based on the number of subjects. And again, smaller boxes indicate smaller N's, and the smaller boxes have larger whiskers, meaning that they have more error. Bigger boxes mean larger N, and they have shorter whiskers, which indicates that they are more reliable. And then the diamond down here says that we find that the effect size is somewhere around 1.5, 1.25, 0.12. So it's positive, it's above 0, so it's a positive effect size. And it's 0.12, and that's a low effect size according to Cohen for Hedges G. So overall, we have an average effect size for all the studies, which is a low effect, but it's there and it's positive. It could be as high as 0.25, which is a moderate sized effect, or it could be as low as almost to 0, meaning that there's no effect. It's 0.17, and it goes down to 0.04. So that's how you read one of these blobographs or forest graphs. Okay, and just a couple things to fill in information for you. Odds ratio. These are for case-controlled studies. So a case-controlled study, you have cancer patients, those who smoked, that's called a case, or that's called exposure, and those who did not smoke, control. So you have a bunch of cancer patients, and you ask them, did you smoke cigarettes? And some say yes, some say no. Those who said yes are considered to be a case or exposed. Those who did not are called control. And the number of case-controlled patients who did or did not have exposure to a factor, the number of controls who did or did not have exposure would be used to create the odds ratio. And what the odds ratios mean is an odds ratio of 1 means there's no association between smoking and the disease. An odds ratio greater than 1 would indicate that smoking would be a risk factor to cancer, and an odds ratio less than 1 would indicate that smoking would be a protective factor against lung cancer, which we know is not the case. And if you want to get really technical, you could use this table to graphically see what we're doing. We talk about those exposed and those unexposed, that is those who smoked, those who didn't smoke, and those with the disease, that is the case, and those without the disease, the control. And then the odds ratio here is you just divide A times D and you divide it by B times C. But that's all you need to know about the odds ratio. And then throwing around effect sizes again, so let's go over these. Pearson's R is an effect size, and the asterisk, I should need to put an asterisk here. means that this is directly from Cohen, the man, and a small one is around 0.1. Medium effect size for R is 0.3, and a large is 0.5. For Cohen's D, and also this would be Glass's delta or Hedges G. They're the same thing more or less. A small effect size would be 0.2, medium 0.5, large 0.8. Partial eta squared is an effect size. Sometimes it's used in a meta-analysis. Small is 0.01, medium is 0.06, large is 0.14. Odds ratio is a small one is considered to be 0.35, medium 0.9, and large 1.44. And Hedges G is Cohen's D when you have small n less than 20. Glass's delta is Cohen's D when you don't have the guarantee of homeoscedasticity. And let me leave you with an example to work on yourself. Oh no, this is another example. I haven't gotten to that yet. Media effects of experimental presentation of ideal physique on eating disorder symptoms, a meta-analysis of laboratory studies. And so here's a table from a meta-analysis, and it's using Cohen's D. Note, D equals Cohen's D, weighted by study size. So we have D, which is Cohen's D, weighted. We have K, the number of experiments, and N, the number of subjects in that experiment. So we have, when we're looking at positive effect for media exposure, that is, a girl saw a media image of somebody with a positive body image, and and then control group where they saw a control figure, and I'm sorry, I got confused there. It wasn't positive image, it was a negative thin image. And when they're exposed to a thin image, the girl's positive affect, that is how happy they feel at the present moment, dropped by 0.49 units, which is a medium effect size. And there was 8 studies that did this type of experiment, and these 8 studies had 202 subjects altogether. And for the control condition, the Cohen's D was minus 0.54. That means that their positive affect dropped a little bit more in the control condition. And then down here for depression, when they're exposed to thin media sources, the D was 0.11, which meant that their depression symptoms increased. However, when they were exposed to the control condition, the D was minus 0.12, which means their depression systems lightened or lessened. So that's how you'd go about reading a data table from a meta-analysis in a published article. And now, second to last, back to the file drawer effect. So when we talk about the file drawer effect, we're talking about reporting biases in the reporting of the research. And there could be several types of biases, and each one can somewhat be analyzed by doing a meta-analysis. Publication bias is whether or not an article is published or not published based on the nature of the research findings. And so a publication bias is our file drawer effect, or the one I've been talking about. But we could also have other reporting biases, such as a time lag effect, which is whether the length of time between the publication of research and the direction of the results. Multiple publication bias, whether or not the single data point is published in one or more than one articles. Location bias, which means that some locations around the world make it more difficult to find articles there, and other locations make it easier to find articles. Citation bias, whether or not the publication is in a citation index or not. That is, whether the article is in PsycInfo or not. For example, when you look up my H index, it says it's 3, and it says I'm at St. Olaf, and that's because most of the publications I've had here at York have been in non-citation publications, and Scopius doesn't find them. Language bias, that is, you may only do meta-analysis or a systematic literature search, on English language journals because you know English and nothing else. And so there could be non-English journals with different types of results. And outcome reporting bias is the selective reporting of some outcomes or not the others, depending upon the nature and the results. That is like a partial or a halfway file drawer effect. You report the significant results you found in your study, that is, you're doing some type of p-hacking, and then you don't report the dependent variables that were not significant. And I mentioned before multiple publication bias. Let me give you an example of this. Melander et al. Looked at this and published in the British Medical Journal in 2003, and they looked at 5 studies on SSRIs, that is Prozac, in Sweden between 89 and 94 for the treatment of depression. And all of these studies, all of these dots here, ended up being referenced in citations and citation indices, so they could be talked about in meta-analyses. But what Melander did was look at how that was biasing the view of things based on just a few studies. So we see here that we have the studies which are circles, and the studies that are blue are non-significant effects. The studies that are red are significant effects. And then we see the green diamonds are standalone publications, and the yellow are pooled publications. And so what we see is that here for drug 5, for SSRI number 5, we see here that the significant effects are only published in standalone journals, and the non-significant effects are not published in standalone journals at all, and we see that again up here with drug 3. However, all of the effects, or all of the individual studies, are published in a pooled report. We see an abundance of red circles leading to green diamonds, which indicates that individual significant studies get published individually, and then what happens is all studies or non-significant studies end up sometimes being described in second hand in terms of the introduction of a paper. And so this is what we mean by whether or not you're getting accurate results based on your library search, because as you can see in this case here, and this case here, and this case here, that is, this one study, or this one study is showing up in 2 different articles, and this one study here is showing up in 1, 2, 3 different articles in these pooled publications. And so it's very difficult to be able to sort out which description in an article is associated to which actual data set. So sometimes you may overcount or undercount. And then to help us understand when we may have a file drawer effect, we can look at funnel plots. Funnel plots are scatter plots of effect size, which is posted on the x-axis, versus study size, which is posted on the y-axis. And if you have a symmetrical funnel, that usually indicates there's no publication bias. And so here's what I'm talking about a funnel plot. We have the effect size on the x-axis, and in this case it's the log of the odds ratio. And then we have the n, or standard error, because n and standard error are related, so we could use either one. The lower the standard error, the higher the number of subjects in the study. And so we find the overall effect of our meta-analysis right here. And then when we plot our results of each study, they show up like this. And it's symmetrical because if you cut the funnel graph in half here, there's just as many over here as there are over here. And here's an example of a symmetrical funnel graph. And here's a example of an asymmetrical funnel graph with lower power studies missing from this area here. That is, as the standard error increases, that means that n is going down and the error is increasing, or the reliability is decreasing. And what that means is this area would be filled with studies that did not support the hypothesis, but were not big enough in terms of the number of subjects to impress peer reviewers to say that even though this is a negative finding, we should publish it, because up here you have a negative finding and you have a negative finding. And number one, up here you're going to have lots and lots of subjects, so you're going to have a low level of unreliability, and that's going to impress people. And also up here you're going to be closer to the average of the effect that we're used to in the field. And so the researchers will say, well, that's kind of close, and that supports the whole idea that things are looking good for this effect. But then down here, you're not going to see anything, because these are not going to have high ends, and so they're not going to be really impressive. And also, they're going to be way out here. And a study, for example, right here is not going to be impressive at all, because it's going to have only a few subjects, and it's going to find a very, very contrary effect size compared to what you want for the actual phenomenon. And so researchers may reject it because it probably has a lot of error in it, or they're proponents of this new theory and they don't want to publish it. Or number three, this is just a really crappy replication and they don't think it deserves to be published. And so the funnel graph in sum can show you where you may have a file drawer effect. Okay, a couple exercises for you. Take a look at Song et al. This is a meta-analysis on Facebook use and depression. And take a look at Table 1. What's the average weighted correlations for time spent on Facebook, compulsive use of Facebook, and non-use of Facebook? Post that in the week 12 discussion board before 6 o'clock tonight. And then once you've done that, think about these things. Identify more reliable studies for each of the three categories. That is, how would you go about identifying the more reliable studies? And then ask yourselves, and this is more a subjective question, Do these more reliable studies agree with the overall conclusions for the three categories, or do they differ? And like I say, post your answers, read other people's answers and discuss. You have until 6 o'clock to finish up. All right, so that's it for today. Post any questions you have in online office hours, and I'll try to answer them as soon as I can. Thank you. Bye-bye.